Last three lectures we have investigated the angular momentum extensively in Schrödinger picture. That is, we have obtained a differential equation for each of the angular momentum operator and tried to get their eigenvalues and eigenfunctions. Today we shall investigate the angular momentum the quantum theory of angular momentum, but this time we shall use the matrix mechanics or Heisenberg mechanics. In we have also applied the theory for the solution of a harmonic oscillator, wherein we found that we do not assume any specific form of the operators, but the starting point is the basic commutator relation, that is Q alpha P beta is equal to IH cross delta alpha beta. And in quantum theory we have worked out the commutator algebra in detail, and we found that the angular momentum operator L alpha, L beta, they do not commute, rather this is IH cross epsilon alpha beta gamma L gamma. And here we are using the Einstein's summation convention, that is, if we write it explicitly, this is IH cross sum over gamma, here it is 1 to 3 epsilon alpha beta gamma L gamma. Now to start with, we used ladder operators for angular momentum, which are defined as L plus minus operator is equal to Lx operator plus minus I Ly operator. It is very obvious that the Hermitian conjugate of L plus is Lx plus I Ly. Its dagger, this is Lx, as it is Hermitian, minus I Ly, that is L minus. That is to say that L plus minus dagger is equal to L minus plus. They are one is the Hermitian conjugate of other. The similar thing we obtain for A plus minus operator. The Hermitian conjugate of the raising operator is the lowering operator, and the vice versa. Here our primary interest is to find out the commutator relation of L with L plus Lz with L plus minus. This is equal to Lz Lx plus minus I Lz Ly. We know that this is equal to IH cross, for this it is epsilon 3 1, and obviously non-vanishing term is 2, and it is Ly plus minus IH cross, and from this we get again IH cross epsilon 3 2 1 Lx. Now what is the value of 3 to 1? This is 3 to 1 is minus 1, and this is plus 1. So we have IH cross Ly, and this is I square is minus 1, and there is another minus 1, so this is plus plus minus plus minus h cross Lx. If we take plus minus h cross common, then it is we find that it is Lx plus minus I Ly. This is equal to plus minus h cross L plus minus. So this is the commutator relation of Lz, and we know that L square, L plus minus, they commute because it is L square Lx plus minus I L square Ly. This is 0, this is 0, so it is 0. So L square commutes with L plus minus. So these are the two important relations that will be of use in future. So so Lz L plus minus is equal to plus minus h cross L plus minus L square L plus minus is equal to 0. This is the information that we have obtained till now. Now we consider the product of L plus and L minus. So what is L plus, L minus? This is Lx plus I Ly into Lx minus I Ly. This is equal to Lx square plus Ly square. Lx square comes from when this is multiplied by this, and Ly square comes from here, and then we have Lx Ly minus IH cross Lx Ly. Be careful about the ordering, and when this is multiplied by this is steady, no H crosses there. So it is, this part we can write it as L square minus Lz square, Lz operator square, and for this is actually, this part is actually minus IH cross Lx Ly, which is equal to this minus I times IH cross Lz. So this is plus H cross Lz. So this term is plus H cross Lz. Similarly, we find that L minus L plus is equal to L square minus Lz operator square minus H cross Lz. So this is again an important relation and will be of use. L plus or minus L square operator Lz operator square plus H cross Lz, and L minus L plus Now we come to the eigenvalue equation. Eigenvalue equation, we assume that we have an eigenket. and the L square operator, the eigenvalue of L square operator is lambda H line square, and that of Lz is alpha H cross. So as per Dirac's bracket notation, the eigenfunction is written by the ket this. Actually this corresponds to phi of theta phi of the Schrodinger picture. So we write eigenvalue equation L square operator operating on lambda alpha gives you lambda H line square lambda alpha, and Lz operating on the lambda alpha ket gives you alpha H cross lambda alpha. These are the eigenvalue equations. Our aim is to find out the values of lambda alpha. We first see what this equation provides us. We have Lz L plus minus is equal to plus minus H cross L plus minus. We operate both the side by the ket lambda alpha and see what is the role of L plus minus when operates on this. The first term is Lz. First term is Lz over L plus operating on lambda alpha. Second thing is L plus minus Lz operating on, and on the right hand side it is plus minus H cross Lz operating on lambda alpha. You see that this part is, as per this eigenvalue equation, is alpha H cross lambda alpha. So we write Lz operating plus minus they had we take this on the other side, so it is alpha H cross plus minus this, so alpha plus minus 1 H cross operating on L plus minus on lambda alpha. If we compare this equation with this, we see that L plus minus, when L plus minus operates on this eigenket, the alpha value is either increased by 1 or decreased by 1. That means L plus minus operating on lambda alpha gives you another state. The normalization constant is this, and then it is when L plus operates on this eigenket lambda alpha, alpha value is increased by 1, and when L minus operates, alpha value is decreased by 1. That is, they are called the ladder operators. That is, starting from one state, if you have a state like this lambda alpha, operation of L plus takes you to alpha plus 1, and twice you alpha plus 2, so you are moving up the ladder. If we operate L minus, you are landed up with alpha minus 1, so you are going down the ladder. That is why they are called ladder operators, or also called the raising or lowering operators. So this is the significance of this, and we conclude that L plus minus operating on lambda alpha have C plus minus lambda alpha. Our primary objective is to find out the state, to find out the multiplicative constant C plus minus. Towards this end, we write that L plus operating on lambda alpha. It is a state which is C plus alpha plus 1. And if we take its Hermitian conjugate of this relation, it is lambda alpha L plus dagger is equal to lambda alpha plus 1 C plus star. So if we take the this is equal to L minus, as I have stated earlier, that is there. So this is L minus. If we take the inner product or scalar product of these, we get lambda alpha L minus L plus Similarly, starting with the L minus equation, L minus operating on lambda alpha gives you C minus lambda alpha minus 1. This has a Hermitian conjugate relation, lambda alpha. This will be L plus is equal to alpha minus 1. Lambda alpha minus 1 C minus star, which gives you since it is a constant module, so this must be greater than 0. This must be greater than 0. We call it equation A and we call it equation B. If we add equation A and B, we get this is greater than 0 because we are adding two non-negative quantities, and it must be again a non-negative one. If you add these two expressions, this part goes, so we have 2L square So we replaced L plus L minus plus this by adding these two terms, and we get the. So when L square operates on this, as per this eigenvalue equation, we get alpha H line square. And when Mz operates on this, first time we get alpha H cross, and when it operates once more, we get alpha square H line square. So we get it as from here we get 2 within this is lambda H line square minus alpha square H line square. Lambda alpha is greater than equal to 0. Since this is the scalar, is taken out, so this is twice H line square lambda minus alpha square, and then we have lambda alpha This is a non-negative quantity because it is the norm of the vector, which indicates that lambda minus alpha square is greater than 0, or lambda is greater than equal to alpha square. That is to say that the minimum and maximum value of alpha is alpha max is equal to plus root lambda, and alpha mean is equal to minus root lambda. So this is the conclusion. So now we have obtained the minimum and maximum value of the projection quantum number. Coming to this equation, we know that this is the relation, so we write it alpha and L minus plus is this L square operator minus LZ operator square minus H line square LZ operating on lambda alpha is equal to C plus modulus square. Now when this operates on this, we have alpha lambda H line square. For this it is alpha square H line square, and for this is alpha H line, and this is alpha H line square. So H line square is taken common. Then we will have lambda minus alpha square minus alpha, and then we will have lambda alpha normalization condition is equal to C plus square. So this gives you C plus is equal to H line lambda minus alpha square minus alpha. Similarly C minus is equal to H line square lambda minus alpha square plus alpha. So we have this equal to H line square square root of lambda minus alpha square, and we will have minus plus alpha of this. Now we come to the determination of the minimum and maximum value of this operator of the quantum numbers. Now, since alpha mean the minimum value of alpha is the L alpha minus, so if we have an eigenkette like this, mean when L minus operates on it, what we shall get? The alpha value will be decreased by 1. So this is a null ket. This is a null ket. If we apply this form, we get that this can be written as H line square square root alpha mean times the null ket times a ket, but this is equal to 0. So we see that alpha minus a lambda minus alpha mean square plus alpha mean is equal to 0. That gives you lambda is equal to mean. Similarly, if we operate L plus on lambda alpha max, this must be 0, which gives you lambda minus alpha max square minus alpha max is equal to 0 or lambda is equal to alpha max square plus alpha max. If we compare two lambda values, so lambda is equal to alpha max square plus alpha max is equal to alpha mean square minus alpha mean. So we write, if this can be written as when this is taken on the other side, or there are two possibilities. One is alpha mean is equal to minus alpha max. Another possibility is alpha mean is equal to alpha max plus 1. But by our assumption, alpha max is the maximum value of alpha for a given lambda. So this is not possible. And we write it is equal to a minus L. So we conclude that alpha mean minimum and maximum value of alpha is related to lambda. So if we use this is lambda value is L into L plus 1. We have not yet said what is the value of what should be the nature of L values. Now you see that if we start with the minimum alpha value, this is minus L, then if we operate it, then we get minus L plus 1, then minus L plus 2, and through this 0, 1, and ultimately we will have L minus 1 and L, a totality of 12 plus 1 values, a totality of 12 plus 1 values. So we see that there will be such values. If we assume L to be an integer, then this 0 value appears. But if we do work with spin quantum number, it will be found later on that one defines. Let me postpone the discussion. What we know about this, that for a given value of L, alpha ranges from minus L to plus L in steps of unity, so it will have 12 plus 1 values. In the case of Schrödinger equation or Schrödinger formalism, we should see that for orbital angular momentum, the quantum number L assumes negative integral values, but in this theory does not provide you such proof that L has to be integer. No, there so far we have worked out there is no clue that L has to be integer. In fact, for when we deal with orbital angular momentum, then one finds that L is an integer that corroborates with the experiment, and there are other angular momentum, as for example spin. Since spin do not have any classical analog, we cannot formulate any differential equation for the spin angular momentum. Remember that the differential operator that we developed for L square, Lx, Ly, Lz or L plus minus, they are based on the Bohr's correspondence principle. That is, we first write the classical expression, then we replace the operator by Hermitian, the dynamical variable by Hermitian operator. But for spin there is no such analog, so we cannot formulate or we cannot have the differential equation, the differential form of the spin operator. In that case, we define a set of three quantities which satisfies the. Let me first write this one and see that that lambda can be written as L into L plus 1, and no clue about this. And if we say call alpha by m, then the relation becomes L plus minus operating on ml. This is equal to H line L into L plus 1 . We know that L alpha, L beta satisfies the commutator relation is equal to IH cross epsilon alpha beta gamma L gamma. This is actually, if we write the operator, it is L alpha L beta minus L beta L alpha. If we define an operator L cross L, then this form is this, and this is again the operator form. So if we write this for x, y, so it is Lx Ly minus Ly Lx is equal to IH cross Lz. This is actually the z component of L cross L operator, z component. So this relation can equivalently be written as L operator cross L operator is equal to IH cross L operator. Any set of three quantities Lx, Ly, Lz, if it satisfies this quantity, is called the angular momentum. We define any set of three operators which operators, so let me call it operator, say S or J, satisfying S cross S is equal to IH cross S and or J cross J is equal to IH cross J is called an angular momentum. Operator. This is the generalized definition of orbital angular momentum. So if we apply this theory to this theory, that is, if we write S plus minus operating on SMS, then we will have H line square S into S plus half minus MS square minus plus MS S MS plus minus 1, and J plus minus operating on JMJ gives you So if we consider this relation, and this relation, we see that for orbital angular momentum, L is an integer. For spin momentum, for a spin of fermionic system, for electron spin, ms is equal to plus minus half. This is guided by the experiment. So S will have half integral values, and in general this is called the total orbital angular momentum, and J is actually written as vector J is equal to vector L plus vector S, and J can have integral or half integral values depending on the number of fermions or boson. For bosonic system, it will be J will have integral values. For odd system comprising of odd number of fermions, J will have half integral values. So this theory, this angular momentum theory, as we have presented according to Heisenberg picture, does not account only for the orbital angular momentum algebra, but it also can easily be extended to spin and total angular momentum operator. By this we end our discussion on angular momentum algebra, and for the next class we shall apply Schrodinger equation to spherically symmetric cases.